Okay, so as promised, I'm going to show you now how to get our K matrix, and I'm going to do this through an example. We're going to go back to a simpler ODE, heat transfer in a rod, where I'm taking my delta T is theta, and then I'm going to have this term here that defines heat convection over the perimeter of the rod. So this ODE is valid over the distance from some value of 0 through x and the endpoint L, so a rod of length L. My boundary conditions, I have a delta T, T naught minus T infinity at x equals 0. So this is temperature on the surface minus temperature of the surroundings. On the other side, I've got this flux condition. So I've got a balance of heat transfer and convection on that side is equal to 0. And in general, I'm going to have some delta T. Theta is temperature minus T infinity, or surrounding temperature. And C is just my parameter of P is perimeter of my rod, K is thermal conductivity area, cross-section area, and this is a thermal convection coefficient. So in this lecture I'm going to set this up for one element, and then in the following lecture we're going to show how we can take two different elements and put them together into a larger finite element system. Okay. We know temperature on this end, we know flux condition on this end. Let's put in some numbers. We've got ambient conditions around room temperature, 120 degrees C on the surface of the end, and here's some material parameters. And you can add in proper units. I'm leaving them off for the sake of brevity. And we have a length of quarter meter. Alright, so again, you're seeing us go from a strong form equation in this integral, we multiply times a weight function, we simplify this down into the final weak form of the equation. Here again, apply your product rule, you manipulate this equation and substitute it in for this term. What that gives you is a weakly distributed derivative over your weight function, your dependent variable, and a set of boundary conditions. So again, keep in mind that this naturally leads to a simple formulation where you solve for some ODE over the rod subject to physical boundary conditions. So you can tie these back to physical measurements and then determine what happens internally. In this case, what is your temperature distribution. Also, we're again going to stick with the Galerkin form where my weight function is my interpolation function. Here's my temperature that we approximate by constants at the nodes for an element E. Here's my interpolation function. So again, these have the same form. Alright, so as we discussed last time, we have a matrix Kij. For this ODE, when you substitute in these relations, you will get a matrix here, and you also have this term for the convection relation. The terms that are left over get lumped into the flux, so you have your weight function or interpolation function, and you have flux Q1, Q2. So this is your matrix form. Now we want to find out explicitly what this looks like for one element. So let's define interpolation functions. And we're also going to do this on a local coordinate. So if I have a rod of length xb and I just want to look at an element inside the rod, I'm going to define a local coordinate x bar where this is 0 at this node, and then as I move forward it has a length of x bar equals h. So h is the length of this element. So here's some definitions on how you relate a local coordinate and global coordinate. If I take a differential, they're equal since this is a constant. Remember last time, or a couple lectures back, we talked about interpolation functions, and if we assume a linear relation of temperature over this element, that gives you a linear interpolation function for phi1 or psi1 and psi2. Plugging those values in, we take derivatives on these, you get a constant 1 over h squared, you get a linear or quadratic dependence due to the convection. This one can be integrated out pretty simply. You integrate this out, evaluate it over 0 to h, and here's what we get for k11. You turn the crank, do this for k12. Turns out due to symmetry, k21 is equal. We get this and this term. So simple integration on polynomials or constants, and ultimately other thing, you can work this out for this case, k11 equals k22. So here's what we get. Here's our K matrix. So it's inversely proportional to the length of the element. Here are the constants, and this is the dependence on convection. So this is what you would implement in a finite element code to look at heat transfer thermal distribution along a rod for a single element. So next time we'll talk about how do you extend that to multiple elements.